All right, so I wrote back on the top of this the same initial value problem of the spring that we had been talking about in the last video. And then sort of we had noted that for this case we had m equal plus or minus 8i, and we wrote out the solution that x would be c1 cosine 8t plus c2 sine 8t. And so for this particular spring, we want to try and find the exact function that defines its behavior for that position release that we discussed. In order to do that, we need to know the derivative to plug into our initial conditions. So I'm going to go ahead and take that real quick. X prime is going to be minus, taking derivative of cosine 8, bringing the argument out, c1 cosine 8t, plus c2, taking the derivative of sine, we pull that argument out, 8 sine 8t. And then for our initial conditions, we have that x of 0 should be 2/3, which is going to be c1 cosine of 8 times 0 plus c2 sine of 8 times 0. Cosine of 0 is 1, sine of 0 is 0. So that just becomes c1 times 1 plus c2 times 0, or c1. So we know that c1 should be 2/3. And then for our second condition, x prime of 0 should be equal to minus 4/3, which is going to be a little bit messier. The derivative condition usually is. So minus 8 c1, oops, when I took these derivatives, I forgot the most important part, which is switching cosine to sine and sine to cosine. The one thing I miss about live lectures is that students will usually interrupt you right away for that kind of thing. So in that case, I've got sine of 8 times 0 plus c2 8 cosine of 8 times 0. And again, sine is 0, cosine is 1, so we're just going to get minus 8 c1 times 0 plus 8 c2 times 1. So in this case, I've got 8 c2 is equal to minus 4/3, or c2 is minus 4/3 times 1/8, and the 4 and the 8 like cancel, so we've got minus 1/3 times 1/2, or c2 is equal to negative 1/6. So then our x of t is going to be, just plugging in the c's, 2/3 cosine 8t minus 1/6 sine 8t. The same thing. So if you wanted to, for any time after 0, you could go ahead and solve that x, plot it out, and know where the spring goes. And because it's a combination of sines and cosines, it's going to like start here at like 2/3, and that means it'll go below, I guess. But it's just going to be that like classic sine or cosine wave for the solution. I want to set up the general form of the next type of spring equation we're going to work with, and then we'll end up solving it more specifically in the next video. But we want to think about the equation for a damped spring now. Oops, that's not how you spell damped. It's going to be given by m x double prime plus beta x prime plus kx equal to 0. And the math is a little bit easier if we make some substitutions. So we're going to call 2 lambda the ratio beta over m, and omega squared the ratio k over m. And in this case, the differential equation is given by x double prime plus 2 lambda x prime plus omega squared x equal to 0. It's the same thing as before, but once we start actually putting our solutions together, this form is just a little easier to work with. We have time, so we'll go ahead and start setting up those solutions. We're going to assume that x is e to mt, x prime is m e to mt, so x double prime is m squared e to mt. That gives us the ODE. 0 is equal to m squared e to mt, x double prime, plus 2 lambda x prime, which is m e to mt, plus omega squared x, which is just e to mt. And when we factor out the e, we get m squared plus 2 lambda plus omega squared e to mt. So the auxiliary equation is going to be 0 equal to m squared plus 2 lambda m plus omega squared. Yeah. And that looks really messy. Remember, we're trying to solve for values m. We pretend that lambda and omega are numbers that we know. Someday we will plug in numbers that we know, and then it would be a little bit easier to work with. But just for now, since we don't have numbers, we can't actually factor this problem. So instead what we're going to do is we're going to use that quadratic formula. And I'm going to need lots of space to simplify, so I'm going to start over here. So that's 1/2 times I'm going to do that down here actually. So it's a x squared plus b x plus c. So it's 1/2 that negative b, that's minus 2 lambda, plus or minus the square root. Oh, and sorry, it's 1 over 2a, but my a is 1, so it doesn't show up. Plus or minus the square root of b squared, so that 2 lambda squared again, minus 4 times a, which is 1, so we ignore it, times c, which is omega squared. So that's our quadratic formula for roots of this auxiliary equation. And we're going to work to simplify that a little bit so that we can say something about what our solutions will look like. So we're going to get, distributing that 1/2 through, just negative lambda plus or minus 1/2 root of, then multiplying here, 2 lambda squared. Remember to square everything, so it's 2 squared is 4 times lambda squared, minus 4 omega squared. And then nothing else changes in this line except for there's 4 inside both terms in the square root, so I'm going to factor that out. And then I can pull that 4 outside the square root. And then 4 halves just becomes 2. And there's not really much more I can do to make this simpler. So this is what my roots will look like. And there's all the different cases that we talked about for solutions in previous videos can actually come from this one formula. So in the next video, we'll talk about all the different values of lambda and omega that can lead to different types of roots or different types of behaviors.